In a previous lecture, we introduced the so-called potential energy for a conservative force. The definition of conservative force is that the work done by that force over any self-enclosed contour is zero. And with that, we can rewrite the work done by this conservative force from initial point to final point as U initial minus U final, with U the newly defined potential energy. Now, why is this desirable? So let's follow up on this. We're going to start with the work-energy theorem, as everybody knows. We need to simplify the left-hand side of the work-energy theorem so that we can hopefully establish a direct link from initial to final state, bypassing all the intermediate steps. And let's see if that's doable. Now, if all the works are being done by only conservative forces, okay, that means either you don't have any non-conservative forces, friction, or maybe friction is present, but it doesn't do any work, in which case we don't really care. So anyhow, if the work from initial to final is done only by conservative forces, then I can rewrite the left-hand side of the equation as Ui minus Uf by the definition of U. Now, that way, let me continue with this. I can now rewrite the work-energy theorem as follows. Ui minus Uf equals delta K, which is K final minus K initial, right? Now, be careful about the order. On the left-hand side, I have initial ahead of final for U, but on the right-hand side, I have final minus initial for K. And with that, we can move both K initial and U initial to the left-hand side, and both K final and U final to the right-hand side. Okay, so basically we make a switch. Okay, we move this guy to this side, and move this guy to that side. So then I have, on the left-hand side, now I have K initial plus U initial. And on the right-hand side, I now have K final plus U final, right? And they're equal. You know what that means? I'm sorry, this is final. The left-hand side only has initial state, and right-hand side only has final state. See, I have now realized what I started out to do, and that is I established a direct link between initial state and final state. This last equation that you see here, there is no mention of the actual steps that took you from initial to final, okay? We have instead established a direct link between initial and final. Not only did we go from initial to final directly, we also found a quantity that does not change as you go from initial to final. And that is the question mark that I wrote here, this question mark. So we know what this question mark stands for now. This quantity, what is this quantity? What is this quantity here? It turns out to be the sum of the kinetic and potential energy, okay? So this is the reason why we introduced this new form of energy, the so-called potential energy. We can now sum up K and U, we get this quantity, which does not change. As you go from initial to final. Okay. And this quantity, the sum of K plus U, has a new name. Let me define E as the sum of K plus U. Okay, and then this simply means that E initial equals E final. So for the first time, we see a quantity that does not change as we go from one state to another state. And then we say this quantity is conserved. Okay, so we have our first conservation law for what? For the quantity E. E is defined to be the so-called mechanical energy. Mechanical energy is the sum of the kinetic and potential energy of the system. Okay, so E initial equals E final, but that is not unconditional. E equals E initial equals E final comes at a price, and the price is, the condition is that the work is only done by conservative forces. Okay, that's the condition. So we can also say all the forces doing work are conservative. Then you have E initial equals E final, and that is known as our first conservation law, the conservation of mechanical energy once again. Okay, let me write that down. Conservation of mechanical energy. It is one of the 3 conservation laws you will be learning in physics 8A. And I've said that before, but I will say it again. You may have different methods to solve a certain problem. But if that involves a conservation law, such as the conservation of mechanical energy, then use it, okay? Almost always, the conservation law gives you the fastest and most efficient path to the solution. Because again, it links an initial state to a final state directly. You don't have to know anything about the path that took you from initial to final. So that's the cleanest way to find a final state if you know what happens in the initial state. Okay, you will see plenty of examples of that. Now, before we do that, let's first take a closer look at this conservation law. Basically, it says that if the forces doing work are all conservative, then the kinetic energy of a system can change, the potential energy of a system can also change, but the sum of K plus U, which is known as the mechanical energy, does not change. So we say it is conserved. This only happens because we have defined the potential energy in such a way, right? We define the potential energy like this. This is how we define potential energy. I mean, actually right here, that's how we define potential energy, right? And if we were to define potential energy differently, if we define potential energy Wi to F equals UF minus UI, which in other words, delta U, then something funny would happen, okay? Then the left-hand side of this equation here would be U final minus UI. And then when you do the algebra, you'll find that the next equation is not going to be K initial minus K, plus U initial anymore. It's going to be K initial minus U initial, which would be equal to K final minus U final. That's funny. Okay, that doesn't make sense, because that would say that it's not the sum of these two energies, but it's the difference between the kinetic and potential energy that doesn't change. That doesn't seem to make any sense, right? So that's how we defined initial, W as U initial minus U final, not U final minus U initial. So that's what the algebra shows. But what's the physics behind it? Okay, you don't want to set up the wrong sign when you use the equation to find U. You want to make sure that the work done is indeed U initial minus U final. You don't want to write down U final minus U initial, even though in the case of delta K, that is K final minus K initial. Okay, if you truly understand what's going on, you won't make that mistake of switching the orders. There's a reason why we do that. As you climb up hills, you are expending energy to gain, and what happens, you're gaining potential energy, right? You're gaining potential energy. Or if you start with kinetic energy, throw a ball upwards, this ball is losing kinetic energy on its way up, but it's gaining potential energy. Now, on its way down, the ball would lose potential energy, but instead it gains kinetic energy. So the total energy remains the same, assuming there's no friction. Okay, so you see, in order to gain kinetic energy, you have to spend potential energy. So that's a trade, all right? So it's a matter of how much energy you spend. If you spend potential energy, you can do work, and that work turns into kinetic energy. That's the essence of the conservation of energy. Now, this means that the work done by the conservative force should be equal to the potential energy spent, okay? Not the potential energy gained. You spend potential energy to do work, and then you can gain kinetic energy. But how much is the amount you spent? Is that the same as delta U? No, delta U is the amount of potential energy gained. Okay, delta means change, which means final value minus initial value, not how much you spent. When you figure out how much you spent, you don't go final minus initial, you go initial minus final. It's obvious to some of us, but it doesn't seem to be obvious to you. If that's not the case, it's not that obvious to you, don't worry about it. We can see a very simple analogy, then you would certainly agree with me that the amount of potential energy spent is initial value of the potential energy minus the final value, not the other way around. We don't use the potential energy, that's a little abstract. We use instead of money as an analogy. You can see clearly why that's the case. Okay, so suppose, let's look at this scenario. Suppose, okay, you go to the mall, all right? So this is what you have before you go to the mall. You have 5 of those $20 bills. Okay, this is what you have, right? You have $100, right? Then you go to the mall, right? You spend some money and you bought this stuff, $80 worth of stuff. Okay, then how much money do you have left? $20. Okay, so you start with 100 and you spend $80, you get $20 left. So then I ask you, how much money did you spend on your shopping spree? You say, oh, I know, I spent $80. But how did you get that $80? What's the math? The math is, well, 100 minus 20 equals 80, right? Actually, 100, yeah, 100 minus 20 equals 80. So you start with $100, you end up with $80. I'm sorry, you end up with $20, you spend 80. This is initial, see, initial number, that's 100. Final is 20, right? Initial is 100, final is 20. And you take the initial minus the final, you get the amount of money you spent, which is this, right? So this clearly shows you that to find the amount of a quantity such as money or potential energy that you spend, you have to take initial minus final. That is the reason why in the definition here, okay, we put initial ahead of final, right? The work done by the conservative force, okay, equals to the amount of potential energy spent, so it's U initial minus U final. And in return, that work can be used to change the kinetic energy. Okay, you spend potential energy, but you gain kinetic energy, and therefore the total energy of K plus U remains the same. So that's how we define potential energy. Okay? So now, once you understand this, you can clearly see why you put UI ahead of UF in the definition of potential energy. That's how it makes sense. Right? So we can see this definition of U allows us to rewrite the work energy theorem into this form, into this cleaner form of E initial equals E final. Okay, this is better than the work energy theorem in its original version because we don't ever have to worry about what happens in between initial and final. We go directly, we jump from E initial to E final because they're the same. So we found something to be remain unchanged as a result of the process going from initial to final. That's the conservation law. Again, this is only a special case of the work energy theorem. The work energy theorem is derived from Newton's second law. As long as Newton's second law is valid, so is the work energy theorem. But as you go from the work energy theorem to the conservation of mechanical energy, it's conditional. Okay, there is a condition attached. There is a string attached. And here is the condition again, once again, it's the condition that all the force that did work must be conservative. Okay, again, if you have totally absence of non-conservative force, such as friction or tension or whatever, then of course you have conservation of mechanical energy. Or maybe you have a tension, have a normal force, you have friction. Does that mean mechanical energy is not conserved? Well, not necessarily. I mean, you have to look at whether these guys did work or not. If friction didn't do any work, if tension didn't do any work, then mechanical energy is still conserved. Okay, so be careful about that. That's the condition for our first conservation law. And then in order to apply the conservation law, we have to know the expression for the potential energy U, right? So this is, this is the formula that allows to find the potential energy. given the force. And we know of at least one example of a conservative force that is gravity, okay, the gravitational force. It is now associated with a potential energy known as the gravitational potential energy. Every conservative force has its own version of potential energy. We'll see another example of conservative force in physics 8a, and that is the force of an elastic spring, okay, an ideal spring, satisfying F equals negative kx. Remember that? Okay, it is associated with what's called elastic potential energy. So in order to apply the conservation of energy instead of the work energy theorem, we must introduce the relevant potential energies, the expressions. So in the next lecture, we're going to look at how we can find the gravitational potential energy as well as the elastic potential energy. And after that, we can put it to use. We can apply the conservation of mechanical energy to solve problems.